Happy day and welcome everyone. So today what we're going to be doing is doing a quick little recap of different of the periodic trends notes. So what are some of these trends? We're going to focus a little bit more on ionization energy and really talking about successive ionization energies, like what happens if you remove more electrons. We're also going to be talking about what it means to be isoelectronic today, as well as what does it mean to be paramagnetic or diamagnetic. So that's going to be our focus for today. Okay, so just as a quick little recap here, we were talking about the fact that all of the trends are pretty much down the periodic table. We say it's due to shielding. Across the periodic table, we say it's the effective nuclear charge. Okay, what is shielding? It's simply the idea that you have more and more energy levels as you go down the periodic table. So we've got more and more shells. So what about effective nuclear charge? It's literally that. It is the effect of the charge in the nucleus, which means you have more and more protons as you go across the periodic table. And those protons tend to pull those electrons in. And so they have an effect on the radius, they have an effect on the ionization energy, that will have an effect on the electronegativity. And so it really plays into any one of these trends that we're going to be looking at. Now, if you remember radius is going to be the easiest one to keep in mind. And if you just remember that the atoms get bigger as you go down, and we're talking about neutral atoms here. They get bigger as you go down. They get smaller as you go left to right. You know that they get bigger because you have more and more energy levels. But if you try to use the reasoning going across, that you say, well, it's because they get smaller because you have less protons and less neutrons and less electrons. Well, that's not actually the case. You actually have more protons and more neutrons and more electrons as you go across. So why is it that they get smaller? Well, it's because you do have more protons. So then why are they smaller? Well, those protons have a stronger magnetic effect on those electrons. So that electrostatic attraction is greater and they pull those electrons in closer. And so as long as the shielding is constant, what we're talking about is just the number of energy levels. As long as the energy levels are in the same shell, then you have to look at the number of protons. And that's how you're going to end up figuring out the size or whatever the trend is. Then we were talking about ions, and we know that if they're positive, they actually get way smaller. That means they lost an electron. Even just by losing one electron, they get a lot smaller. If they gain an electron, similar to like fluorine here, gaining an electron, see that it practically doubles in size. And so again, you don't want to use the idea that it's increasing in energy level. We want to say that just by simply looking at the proton to electron ratio, what happens to that? The more protons you have, the stronger the pull's going to be. But if your protons and your electrons are equal to each other, that's going to be your neutral atom. Okay. Then we got into electronegativity, and we were talking about how it's just an atom's ability to attract another atom's electrons. And the trend is the opposite. As you go down the periodic table, it actually decreases, and as you go across, it increases. So opposite from radius. The one thing to remember, and this always helps, is keep your atoms away from fluorine, okay? Fluorine's going to steal an electron away. Fluorine's got a really, really high electronegativity value. It's the highest on the chart. It's a 4. And so that kind of helps because we know that it increases going this way, but then it must be decreasing going down the periodic table, okay? All right, so then we were talking about electron affinity. Very similar to electronegativity, where we're talking about adding an electron, but there's actually energy associated with this now. It's measured in units of kilojoules per mole, and it can be positive or it can be negative. So when is it positive? Positive means that it doesn't happen unless it actually absorbed energy for it to happen. So we need an outside source of energy in order for it to happen. Whereas if it's a negative, then that will just release energy on its own. It's making it more stable. And so we looked at the difference between lithium and beryllium, where lithium has a negative 60 electron affinity, whereas beryllium's is a positive 66. Why? Well, when you add an electron to lithium, it actually makes it slightly more stable because it fills that S sublevel. Whereas beryllium already has a filled S sublevel. When you add an electron, it actually opens up a whole nother sublevel with one teeny tiny electron in it. And so beryllium's going to fight you on that, okay? So again, if it's positive, that means it requires energy, just like we did with thermal. And if it's negative, it releases energy. actually, they don't really do too much with trends on electron affinity. Typically what happens is they give you the values and then you're asked to explain, okay? All right. Ionization energy. So we know already a good amount about ionization energy from photoelectron spectroscopy. So we know that it's the energy that is required to remove the outermost electron, okay? But it doesn't have to be. You can actually have multiple electrons removed, but they do start with the outside ones and then they pop those off and then they keep on going down, and we'll talk a little bit about that in just a second here. Okay, so what's the trend? Well, the trend is when you go down a group, again, it's opposite of radius. So as you go down a group, it actually decreases. And so we can do a down arrow versus if you go across a period, it increases. We said before, shielding is going down the periodic table, whereas if we're going across the periodic table, we know that we call that the effective nuclear charge, or the ZEF is what people will call it. Now, AP's not okay with that as an explanation, so for shielding, we want to start off by saying the more energy levels that we have, then that's going to have an effect on it. Now, what happens when we have more energy levels? We want to make sure, yes, that means that the electrons are further away from the nucleus, but we want to talk about the energy it takes to remove the electron. Well, if you're all the way out here at a concert, for example, and someone says, hey, let's go, we got to go to the bathroom, you're going to take off and leave. But if you're really close to the center attraction, which is your nucleus, you're going to have a harder time leaving. There's a stronger attraction there. So the more energy levels, the less energy required to remove an outer electron. Okay, versus if we're looking at going across the periodic table, we always say that now we're talking about having more protons in the nucleus. And the more protons we have, the stronger the attraction. And if it's a stronger attraction, the more energy that's going to be required. So we can even put in parentheses if we want here that there's actually a stronger attraction. And so then what happens is it requires more energy to remove an electron. Okay, so now the question is, can we explain it? If we see on here, it says explain using Hund's rule why magnesium has a higher ionization energy than, let's say, aluminum. Okay, and we can see on this graph that definitely there's something funny happening here. Now, a lot of students will say something that's totally wrong. They'll say, well, because the trend is that it decreases as you go left to right across the periodic table. That's wrong. It doesn't, okay? So what is happening here is, let's figure it out. Let's draw the best thing to always do anytime you're asked any of these FRQ essays is to try to draw pictures, okay? And so anytime it has anything to do with atomic theory, then I will draw a picture of trends or anything like that. I'll draw an electron configuration and use Hund's rule, okay? So we've got magnesium, and magnesium's electron configuration I know is going to be neon with its 10 electrons, and then it's got a 3s2 versus aluminum is going to be also neon, 10 electrons, but now it's a 3s2 3p1. Okay, so if I draw magnesiums, it's a 1 up and a 1 down. If I draw aluminums, it's going to be, yes, a 1 up and a 1 down, but then my P has 3 orbitals in that subshell or sublevel, and then I have 1 electron in there. And what they're saying is it actually requires less energy to remove this 1 electron than it does to remove this one. And so the question is, why? Well, again, just like we said before, if we have a full sublevel, magnesium we can see has a full S sublevel, and because that S sublevel is filled, it actually makes it slightly more stable, which means it requires more energy to remove that electron. Requires more energy to remove the electron. Okay, now, the next question is, what about phosphorus versus sulfur? Because something a little bit different is going to be happening with phosphorus versus sulfur here, okay? Well, let's draw it and let's see what happens. So we've got phosphorus, it's still neon, 10, but then we've got 3s2, 3p3 versus sulfur, and sulfur is going to be very similar, except for it is a 3s2, 3p4. Okay, so we still have neon with the 10, and so now we've got 3s2 and 3p4. Okay, so let's draw this out. So I have my S is filled here, and then my P, I've got 1, 2, 3, and then I'm going to fill my 3 electrons in there. For my S again, for sulfur, I have 1 up, 1 down. And then my P again, I've got 1, 2, 3, but then I have a 4th one there. So what this is saying is this 4th electron right here requires less energy to remove. So if it requires less energy to remove, why? Well, this is weird. It's not a full S sublevel, but it's half full. For some reason, the scientists have done these calculations based on probability, and they have said that if it's a half full sublevel, it actually requires more energy to pull off. So it's slightly more stable to have a half-filled S sublevel, or in this case, it's a P sublevel. Okay, so then that makes it a little bit more stable. All right, so then the next thing that we're talking about on here is there are successive ionization energies, and removing the second electron from an atom always requires more energy than the third, and that's higher than the second, and so on. So your 4th is higher than the 3rd, the 5th is higher than the 4th. Why does ionization energy always increase as more electrons are removed? That's the question, okay? Well, just like we said before when we were forming ions, once you pull 1 electron off, the size of the atom decreases by like half because the attraction is so much greater. That proton to electron ratio has increased, and because of that, it actually draws the electrons in closer. Every time you pull an electron off, it actually makes it harder for those electrons, those next electrons to come off. So why does it always increase? Because of our proton to electron ratio increases, making the attraction greater. Making the attraction greater. And when I'm talking about which attraction, I'm talking about the electrostatic attraction, the protons to the electrons, greater. And if that's greater, then that means it requires more energy to pull those electrons off, okay? So it requires more energy. Oops. So it requires more energy to remove the electron, another electron. Okay, and so that's kind of the idea, is it ends up increasing. So let's take a look here and just look at the graph and the way that this is working out. You can see this here. Now, there's something in this light blue color that I want to make sure that we pay attention to, okay? You can see that sodium, yes, it increases, okay? Magnesium, yes, it increases. And aluminum, we can see, yes, it increases every time, just like we said. Every time you pull 1 off, so I1 is removing the first electron, I2 is removing the second. Why is it that there's all of a sudden a huge jump at certain points? This is incredible. Where does the huge jump happen? The huge jump, what I'm calling like this huge jump that happens, it happens when the valence electrons are gone. The huge jump takes place once the valence electrons are all removed. Then the next electron after that is going to require a lot more energy to be able to pull off. So that's when that huge jump happens. What do I mean by valence electrons? Well, sodium only has 1. So it's we said that it was neon, and then it's a 3s1. Well, losing that 1 electron, now that energy level beneath it is completely filled, just like neons would be, okay? And magnesium, same thing. Magnesium has 2 valence electrons. So once it loses those 2, that third one, it's going to fight you really hard on. It's fighting on any one of these, okay? So we said ionization energy is always positive, but even more so, okay? So why do you think the shaded area, or what do you think the shaded area is representing? That's after all of the valence electrons have been removed. It's again that jump after those outermost electrons are removed. The energy jump happens after all the valence electrons have been removed. And so we said, for example, aluminum is 3 valence electrons, so we see a big jump once we remove the 4th electron. Okay. What does isoelectronic mean? Oh, and by the way, I also wanted to mention really quickly here, I wanted to take a look at the difference between argon and potassium. Okay, now, we know that argon's a noble gas, so argon's going to have a really high ionization energy. It doesn't want to lose its electron, any of its electrons, okay? So it loses one. Now, potassium has 19 protons, so let's kind of write this down here. So we know that potassium has, if it's neutral, it has 19 protons, and it also has 19 electrons, okay? So it loses one of its electrons, and the value is 419. Now, after it loses one of its electrons, it has the same number of protons, but now it has 18 electrons, which is the same thing as argon. Argon has 18 electrons. So why is it, if we compared argon, if they have the same number of electrons, they both have 18 now, look at argon's value is 1521 to be able to remove that 18th electron, whereas if we actually look at potassium's, it's 3051? What? It's like practically double the amount to remove the same electron, the 18th electron. Why? Aha! If you're thinking because it has more protons. Argon only has 18, potassium has 19. So if they have the same number of electrons, then that's going to be the case. Now, what is the term for this? It's called isoelectronic. Break it apart. Iso means the same or equal, and electronic is referring to the electrons. So what isoelectronic means is when two atoms or ions have the same electron configuration, same number of valence electrons and everything. So it's got the same electron configuration. Now, I also want you to keep in mind, but if they're isoelectronic with each other, it's probably saying that their number of protons are different though, okay? So they do have a different number of protons, so their nucleus is different. And remember, that's the identity of the atom, so we do need to make sure we look at that. It says list 3 ions that are isoelectronic with argon, okay? So if we look at a periodic table, so let's just glance back here real quick because I did want to do this as well as labeling the periodic table real quick here. So we know that on the far left here, we have our alkali metals. Then we have our alkaline earth metals. So this is also part of the unit, is making sure that you know the names of these groups. This whole section here in the middle, we call these the transition metals, whereas down on the bottom, we call those the inner transition metals. So these are the transition metals. Down on the bottom here, we call these the inner transition metals. Okay, and then let's go to the far right. We know that everything to the right of the staircase, we know those are nonmetals, okay? But what are the names of the families? So these here we know are called the noble gases. Then we were talking about under fluorine, these are called the halogens. Those are called the halogens. And so the halogens are right under fluorine. Now, the rest of them, we just say, like the metalloids, for example. So they're either metals, nonmetals, or metalloids. And aluminum is not included, but the metalloids are the ones that basically are going to line up your staircase. So your staircase starts here between boron and aluminum, and then it keeps on coming down. So anything that has a bolded line with that's considered a metalloid. Oxygen family, those are also called the chalcogens, but we don't really use that very much. Okay, so what they're asking us is they're saying, take a look at argon, and what's isoelectronic with argon? Okay, well, I know that argon has 18 protons, but I'm not talking about that. I'm talking about the electrons. So what can have 18 electrons? Well, nothing else, at least not in its neutral state, but if chlorine gains 1 electron, it'll have 18 like argon. So Cl minus 1. If sulfur gains 2, it'll have 18 like argon. What about the other end? Well, potassium, if potassium loses 1 electron, instead of having 19, it'll have 18 like argon. So that's all it means to be isoelectronic, is to have the same number of electrons. Okay, so it was asking us here to list 3 that are isoelectronic with argon. So let's just put down chlorine with a -1. Let's put down potassium with a +1. And then we can put calcium with a +2. Okay, so those are all going to be isoelectronic, meaning they have the same electron configuration. Okay, let's wrap this up here. When we're going top to bottom, we know that it's always due to shielding, and so we say the more energy levels that it has. Okay, when we're going left to right, we say that it's due to the effective nuclear charge, or ZEF, and so we say the more protons that it has in the nucleus. Electronegativity, as we go top to bottom. Now, I like to fill in radius first because I know that radius increases. And so if this increases, then these 2 must decrease. Versus on this one, I know that left to right, it decreases, which means the other 2 must be increasing. Again, don't forget, electron affinity can be a little bit different. We don't really talk about the trends of that. Okay, last thing, paramagnetic versus diamagnetic elements. Okay, so it's super easy to remember. Just a couple of things about it. When you hear the word para, like in the word separated, okay, I want that to be your key. That means that the electrons are unpaired, separated, okay? So para, please do not mix that up and say para sounds like pair. Wrong, okay? Para is like separated. Diamagnetic, di means 2. That means that they are all paired. Your electrons are all paired, okay? And so what you do is you draw Hund's rule and you check to see if the electrons are paired or unpaired, and that basically is going to tell you whether it's paramagnetic or diamagnetic. Now, what does it mean? If there are unpaired electrons, then that means that they're going to be attracted to a magnetic field. If there are no unpaired electrons, then they either have weak or no attractions to the magnetic fields, okay? And so it says, draw the orbital occupancy diagrams for the following, indicating whether they're paramagnetic or diamagnetic, okay? So we know that helium is a 1s2, so if I were to draw that, I'm just going to draw 1 up and 1 down. Then beryllium is 1s2, 2s2, okay? Lithium is a 1s2, 2s1, and nitrogen is going to be a 1s2, 2s2, 2p3. Gives us a total of 7, atomic number of 7. Okay, so let's draw these orbital occupancy diagrams. So I have 1 up, 1 down for beryllium, and then I have my s2, which is also 1 up and 1 down. For lithium, I have 1 up, 1 down, but then in my 2s, I only have 1 up. Nitrogen, okay, I have my 1s2 up, down. I have my 2s2 up, down, but then my 2p3, I actually have 1, 2, and 3 electrons in there. So which ones are going to be the ones that are diamagnetic versus paramagnetic? Well, I can see here that these 2 are all paired up, and so if that's the case, that's going to make these diamagnetic, versus the ones down here, these have unpaired electrons, and so if they're unpaired, we're going to say they are separated, and so that's going to be paramagnetic. And remember, if it's paramagnetic and it has the unpaired electrons, then that's where we say that it is going to be attracted to a magnet, whereas if it's diamagnetic, either it's no attraction or a weak attraction. Okay, so let's watch this video. This is a professor from UCLA, and he's going to talk about magnetism.
You might not think of water as being magnetic, but it is.
What?
And so are graphite, aluminum, and glass.
Oh, surprise.
This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet.
Okay, let's pause for a second here. They're saying that aluminum is a good paramagnet. Okay, so if we were to draw the electron configuration, we would, and use Hund's rule, we would actually see that, yes, aluminum does have an unpaired electron. And so because of that, it's going to be attracted to a magnet. So again, he said that it is a little bit weaker. Okay.
so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later.
Okay, now I do want to make sure that I just kind of give you a little bit of a disclaimer here because sometimes molecules do work a little bit differently. So if we were to look at oxygen, they're not talking about oxygen as the atom O. So sometimes it's different. They're talking about O2, okay? And so what happens is the orbitals hybridize with each other, and so sometimes the atom might be where it's, paramagnetic and it has unpaired electrons, but the actual molecule isn't. So in this case, it is paramagnetic, meaning that it has unpaired electrons. But again, we're talking about the molecule. We're not talking about the atom. Okay.
Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet, like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
Okay, awesome. Thank you, Professor. So that's it. That's periodic trends. I hope you guys have enjoyed this and have a happy day.